Hello, welcome to CAMEX University Research Symposium Virtual Presentation 2020. Today I'm going to present a research topic, comparison of dispersion, weightability, viscosity and mechanical properties of unsaturated polyester nanocomposite consisting vinyl silane and dichlorodimethylsilane silane treated aluminum nanofibers. So let me introduce myself first. I'm Subash Panta, student of Texas State University with a degree program Manufacturing Engineering. I'm involved in activities. I'm a Texas State SAMPE Student Chapter Treasurer, also active member of Society of Plastic Engineers. I have won the award SAMPE University Leadership Experience Award 2020, and I'm also a third place winner in undergrad categories from Society of Plastic Engineers 2020 Student Poster Competition. So today I'll be talking about introduction, material system, experimentation, results and discussion, future works and scope, and conclusion about my research. Introduction. Unsaturated polyester resin has a global application in electronics, marines, aerospace, automotives, load bearing, boreholes, tanks and pipes, and oil. Application of unsaturated polyester is in wide range because of good mechanical properties, dimensional stability, and resistance to chemical and cheap cost. Future of unsaturated polyester is to make advanced composite out of it by introducing nanotechnology. Nanofiller added unsaturated polyester has a large surface area to volume ratio. Nanofiller makes multi-phase nanocomposites, provides bizarre mechanical, electrical, magnetic, and thermal properties. But addition of nanofiller is challenging in unsaturated polyester because of lack of proper dispersion, which creates agglomeration of nanofiller in resin. So to overcome this challenge of agglomeration, surface functionalization of nanofiller is necessary by introducing an organic layer into inorganic nanofiller, which creates a better interfacial bond between nanofiller and resin. In previous research, vinyl silane was used as surface treatment, but current research, dichlorodimethylsilane is used as surface treatment of nanofiller, that is aluminum nanofiber. So this research is basically comparison with previous research of vinyl silane treated aluminum nanofiber. Silane treatment of aluminum nanofiber. So in silane treatment, dichlorodimethylsilane is treated with aluminum nanofiber with toluene to 50 ml. So after we obtain silanized aluminum nanofiber, we dry it in oven and dispersed the aluminum nanofiber through roll mill. Objectives of research. To obtain proper dichlorodimethylsilanized aluminum nanofibers. Next, to obtain homogeneously dispersed silanized aluminum nanofiber modified polyester resin. Similarly, to get better mechanical property of dichlorodimethylsilanized treated aluminum nanofiber modified polyester in compared to neat polyester sample. Also to get better mechanical property of dichlorodimethylsilanized treated aluminum nanofiber modified polyester in compared to vinyl silane treated aluminum nanofiber. Challenges for the research. Proper dispersion technique of nanoparticles is great challenging for the research. Agglomeration of aluminum nanofiber in unsaturated polyester resin after dispersion is next challenge. Similarly, selection of proper silane coupling agent to overcome the challenge of agglomeration is also next problem. Material system. Unsaturated polyester with a viscosity of 396 centripoise from Interplastic Corporation. Aluminum nanofiber with a minimal aspect ratio 18:20, trade name Nafin from ANF Technology, and MEKP and cobalt naphthenate as a curing agent. Sample fabrication. Dispersion of dichlorodimethylsilane treated aluminum nanofiber modified polyester was done on 3-roll mill at gap set of 25, 15, and 7.5 micron. Samples were casted in silicon molds, cured in oven at 80 degrees Celsius and post-cure at 110 degrees Celsius. Experimentation for fabricated sample. TG analysis, weightability test, mechanical testing were conducted for the fabricated sample. So in mechanical testing, tensile test according to ASTM standard D638, flexure test according to ASTM standard D790, and isotope impact test according to ASTM standard D256 is conducted. So TC analysis is done to ensure that aluminum nanofiber is properly silanized with dichlorodimethyl silane treated aluminum. And weightability test is conducted to check the weighting contact angle made by resin with substrate. So this is the overall setup of the experiment. The first one shows the silanization of aluminum nanofiber with dichlorodimethyl silane. And then after we obtain dichlorodimethyl silane, dispersion using 3-roll mill is done, and then TG analysis. The fifth one is about doing contact angle test. Sixth one is about fabrication of samples using silicon mold for isoid, tensile, and flexure. And the seventh one is about doing mechanical testings. TG analysis report. Sample amount of 6.25 milligram was done for TG analysis at the rate of 20 degrees Celsius per minute. TG analysis result shows the presence of silane agent dichlorodimethyl silane. The higher weight loss is seen because of properly grafted dichlorodimethyl silane in aluminum nanofiber. The curve at 80 degrees Celsius to 100 degrees Celsius temperature provides the presence of dichlorodimethyl silanized aluminum nanofiber. Next one is weightability results. So in weightability test, we are going to compare the results with dichlorodimethyl silane treated versus vinyl silane treated. So from 0 to 1 weight percentage, vinyl silane treated aluminum nanofiber shows the better contact angle of 32.18, but in terms of dichlorodimethyl silane treated, the contact angle was better at 0.25 weight percentage, that is 62.50 weight percentage. After the loading level starts increasing, the contact angle also increased. Results discussion. 0.25 weight percentage shows lower contact angle comparing to other weight percentage. On the increasing loading level of aluminum nanofiber, the contact angle also increased. It's because of agglomerated aluminum nanofiber on the resin. Vinyl treated aluminum nanofiber shows better property of contact angle compared to dichlorodimethyl silane treated. The lowest contact angle of vinyl treated was 32.18, and that of dichlorodimethyl silane is 62.50. So vinyl silane showed better property of weightability because the silane agent weighted all surface of ANF properly compared to dichlorodimethyl silane treated. Overall, contact angle test is necessary to find out weighting property of resin. The lower the contact angle, better the weighting property of resin in the reinforcement. Mechanical property. So in terms of mechanical property, tensile test was done according to STM standard D638, and from tensile test, tensile strength and tensile modulus is calculated. Similarly, for flexure test, flexure strength is calculated, and from isoid test, impact energy is calculated. Tensile test results. Ultimate tensile strength shows a 0.50 weight percentage of dichlorodimethyl silane treated aluminum nanofiber better properties comparing to other. The trend of ultimate tensile strength starts decreasing as the loading level is increasing. Similarly, 0.50 weight percent is optimum level for dichlorodimethyl silane treated aluminum nanofiber modified polyester in terms of better tensile properties. So from the chart, we can see at 0.508 percentage, the ultimate tensile strength is 48.09 megapascal. But at 1 weight percentage, the tensile strength is 37.122 megapascal. So absolutely at 0.50, the tensile strength is far better than 1 weight percentage. But after the loading level increasing, after the loading level starts increasing from 0.5 to 1 weight percentage, the trend is decreasing in tensile strength, that because of agglomerating aluminum nanofiber. Tensile modulus. The value of tensile modulus is consistent with ultimate tensile strength. Tensile modulus is higher at 0.50 weight percentage than other loading levels. Decreasing trend of tensile modulus is seen as the weight percent starts increasing. So as in 0.50, we can see the tensile modulus is higher than all other weight percentage. So 0.50 is higher, and at 0.75 and 1% the tensile modulus is low. That's because all the alumina nanofiber is agglomerating in the resin. So if we compare the tensile strength of dichlorodimethylsilane treated versus vinyl silane treated, dichlorodimethylsilane treated alumina nanofiber modified polyester shows better tensile strength properties in compared to vinyl silane treated alumina nanofiber. In terms of vinyl silane treated alumina nanofiber, the maximum tensile strength was obtained was 38 megapascal in 0.25 weight percentage. Similar in 0.50 weight percentage is 30 megapascal, and 0.75 weight percentage 24 megapascal, and at 1 weight percentage 41 megapascal. So the vinyl treated aluminum nanofiber didn't show proper tensile properties. But in terms of dichlorodimethyl treated aluminum nanofiber, in 0.50 weight percentage, the tensile strength is 48 megapascal. But in vinyl silane at 0.50 weight percentage, the tensile strength is 30 megapascal. So dichlorodimethyl treated aluminum nanofiber is far better than vinyl treated aluminum nanofiber in terms of tensile properties. Flexure test. Flexure test result shows samples containing 0.50 weight percentage aluminum nanofiber having the maximum flexure strength in compared to 0 and 1 weight percentage, about an average of 85.91 megapascal. But after 0.50 weight percentage, flexure strength decreased with increasing loading level of aluminum nanofiber. It may have happened because of crack propagation caused by agglomerating aluminum nanofiber in resin. Comparing to vinyl silane treated aluminum fiber, dichlorodimethylsilane silane treated showed better flexure properties. So from the graph, we can see at 0.50 weight percentage, the flexure strength is 85.91 megapascal. So from 0 to 0.50 weight percentage, the flexure strength is in increasing trend. But after 0.50 weight percentage, the flexure strength is in decreasing trend. So we can figure out that 0.50 is the optimum level of aluminum nanofiber that we can use to get a better flexure properties. And at 1 weight percentage, the flexure strength is far lower than other loading levels, because at 1 weight percentage, the aluminum nanofiber is highly agglomerating in the resin. So comparing the results of dichlorodimethyl treated aluminum nanofiber versus vinyl silane treated aluminum nanofiber, dichlorodimethyl treated aluminum nanofiber modified polyester showed the better flexure strength properties than vinyl silane treated aluminum nanofiber. So in terms of dichlorodimethyl treated aluminum nanofiber, at 0.50 weight percentage, 85 megapascal of flexure strength was obtained, but in terms of vinyl silane in 0.50 is in between 60 to 80 megapascal. So dichlorodimethylsilane silane treated is far better than vinyl silane treated in terms of flexure properties too. Next one is isoid impact test, which was done according to ASTM standard D256. The test was done in machine instron, test type isoid impact test height 500 mm, test maximum energy of 14 joule, and samples were fabricated with a loading level of 0, 0.25, 0.50, 0.75, and 1 weight percentage. The samples width at notch is 11.50 mm, thickness of 4 mm. Isoid impact results. Dichlorodimethyl silane treated aluminum nanofiber modified polyester didn't absorb impact energy compared to control sample due to crack propagation initiated by agglomerated aluminum nanofiber in resin. In case of loading levels, 0.75 weight percentage absorb maximum impact energy compared to other. As the loading levels increased to 1 weight percentage, the impact energy decreased with higher value from 0.48 kilojoule per meter square to 0.23 kilojoule per meter square. So if we compare the isoid impact results with vinyl silane, then vinyl silane shows better property of impact absorbing than dichlorodimethyl silane treated. So in case of vinyl silane, the impact energy is 1.80 kilojoule per meter square. But from dichlorodimethyl silane, the only impact energy, the maximum impact energy was 0.48 kilojoule per meter square. So vinyl silane treated aluminum nanofiber modified polyester absorbed impact energy better than dichlorodimethyl silane treated aluminum nanofiber. The future work for this research is more concerned about getting properly dispersed aluminum nanofiber in polyester by doing various dispersion techniques using sonicator or high shear mixture. Fabrication of composites panel out of dichlorodimethyl silane treated aluminum nanofiber modified polyester and analyzing the mechanical property is also going to be another future research. And also choosing different forms of silane coupling agent as an organic layer in inorganic nanofillers. So as a conclusion, surface treatment did enhance the bonding between nanofillers and matrix. In context of mechanical properties, tensile strength and tensile modulus was higher at 0.50 weight percentage. Flexure strength was higher at 0.75 weight percentage, but no significant improvement was noticed on impact energy. Maximum flexure strength of 85.75 megapascal was achieved at 0.50 weight percentage, but on increasing loading levels of aluminum nanofiber, the strength decreased. Overall, on comparison to vinyl silane treated aluminum nanofiber, tensile strength and flexure strength were improved by dichlorodimethyl silane treated aluminum nanofiber modified polyester resin. So I would like to thank Dr. Jitendra Tate as a research advisor for this research, Mr. Tim Ferdinand of ANF Technology, Mr. David Gerald of Interplastic Corporation, all team members of Advanced Composite Lab of Texas State Universities. So here are my references. Thank you.